Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. So this video is the next in our series where we have been comparing the means of two populations. Now, up to this point, we have been dealing with two independent populations. We have taken a random sample from each population, calculated the mean for each sample, and then used the difference between those two means as our unit of analysis for confidence intervals and hypothesis tests. This video examines a different technique, the matched samples t-test. The matched samples technique forms much of the foundation of experimental research. In this method, the samples are not independent. In fact, many times each sample is comprised of the same subjects or objects. So let's say we wish to test a new training program at our company. Therefore, we give a group of employees a pre-test about their knowledge concerning a company policy or how to work a certain piece of equipment. We conduct the training and then give a post-test to the same employees. Is there a difference in the scores before and after? Now, another example could be on the production floor. Let's say there are 10 stations in an auto plant where engines are machined. Now, a software upgrade for the machines is being considered that may speed up the process. So each machine is sampled before the software upgrade and then again after the same 10 machines. Is there a difference in machining time? That's what we hope to find out. So as you can see, the units of comparison are not random. They are the same, both before and after. And that, at its heart, is what the matched sample t-test is all about, paired differences. Now, the pairs do not always have to be the same thing, but they often are. They can be paired by some other criteria, but the main point is that they are not independent. So let's go ahead and learn more about the matched samples t-test. Now, to fully understand the topic of this video, you will need to have had experience with or have knowledge of the following concepts: what point estimators are, what sampling distributions are, what the standard error is, what the margin of error is, what confidence intervals are, and finally, how to find the t-values for a given alpha level and sample size / degrees of freedom, both one-tailed and two-tailed. So basically what I'm saying here is that you need to know how to use the t-table. So this video is an extension of all these topics and sort of a weaving together of all of them in the context of analyzing the difference between these two populations using samples. And more specifically, they are matched samples. So let's go ahead and take a look at a graphic. Now, the example we're going to use in this video is about a fictional weight loss program. So we're going to use some matched pairs hypothetical data. So let's say we have 10 men, and we're going to use men because we never talk about a woman's weight, do we? So we're going to use 10 men, and we have their distribution of weights beforehand. Then, of course, we're going to have their body weight after the weight loss program. So it may be down here where the blue distribution is. So what we're going to do is we're going to look at the before and after of each participant. So let's say our first participant has his weight here, where W1 is in the before distribution. And then after the weight loss program, he is down here in the after distribution. So you can see it appears his weight decreased, which is a good thing. Now the distance it decreased is this much, as represented by the red arrow. So his weight decreased by the distance of that red arrow. Now let's say we have participant number 2. So his weight started here where W2 is in the before distribution. Now over the course of the weight loss program, his weight actually increased by this much. So that is our second difference. So D1 is our first difference between those two measures of the same person, and then D2 is the difference between the measurements of person 2. Now person 3 comes along, and their weight starts here, where W3 is. Now after the program, his weight is down here where W3 is in the after distribution. That's quite a difference. So D3 is his weight loss during this program. As you can see, it's quite dramatic. Now the question is, what is the average difference for these three individuals? And remember, it's the same individual before and after. So what we could do is just measure the distance of those lines. Of course, we subtract the green from one of the reds because it's the opposite direction. And it actually comes out to about this. So the length of this orange line shows that on average there was a weight loss, and it was about this much. Now, of course, the length of these arrows do not have any meaning in terms of pounds right now. All I'm trying to show you is that what we're doing is we're matching a before and an after for each individual subject in this study. And then we're finding the average distance based on where they were before and where they were after. So this is called the Fight the FLAB program. So a new diet and exercise craze called Fight the FLAB has hit popular culture. Now, while on this diet, you can eat anything you want every 2 hours, but the item can be no larger than the size of your closed hand. You must also exercise for 30 minutes 3 times a week at a minimum. To test how well this program works, 10 men are randomly selected to participate in a study. They are to follow the program for 1 year. Body weight measurements will be taken before the diet begins and again after 1 year. At the end of the study, we will test whether or not there has been a significant reduction in mean weight for the 10 men by comparing before the diet weight and after the diet weight. So we're looking at the same 10 individuals before and after, and they're only being compared on their own measures, not anyone else's. So we have the before diet program and the after diet program. So before the diet, they could eat a big plate of nachos. Now after the diet program, they cannot. So all that stuff is out of the way, and they have a nice green salad. So what we're doing, we're looking at subject 1. So we calculate his weight before the diet and then again after the diet. Then we have subject 2, and we have his weight before the diet and then his weight after the diet, and so on and so forth for all 10 subjects. Now what is our assumption here? We're assuming that the mean of the matched differences is 0, and we'll have a chart here in a minute that will make that more visible. But our assumption is that the difference between before weight and after weight for each person calculates to a mean of 0. Now what about independence? Remember, these two measures are not independent of each other. They are matched, in this case, to the exact same person on the before weight and the after weight. So weight before is the subject weight before the diet, weight after is the subject's weight after 12 months. So here's what we're really talking about doing. We take a measurement of the subject's weight before the diet, then we take a measurement of the subject's weight after the diet, after 12 months. We then find the difference between those two measurements. So we'll call that D1, D2, all the way up to D10. That is the difference. So of course we'll return to step 1 and repeat the process for all 10 subjects. We then conduct our analysis on this new variable, which is the mean of these 10 differences. And we represent that with D bar. So what is our hypothesis? Remember, the research hypothesis, the alternative hypothesis, is that the Fight the FLAB diet reduces our subject's weight. That is, that the mean of the differences is less than 0. Now notice that is a research hypothesis, therefore it is our alternative hypothesis. Therefore the null hypothesis has to be the opposite of that. So our hypotheses look like this. Our null hypothesis says that the mean of those differences is greater than or equal to 0. So in real world terms, that means that overall our subjects gained weight or stayed the same. Now the alternative hypothesis is our research hypothesis, and that is that the mean of their differences is less than 0, which means overall our subjects lost weight during the diet program. Now we're going to choose a significance level of 0.05, so that is our alpha level. Now since this is a matched pairs t-test with a sample size of 10, we're going to use the t-distribution with degrees of freedom of 9. So in this matched pairs case, our degrees of freedom are n-1. In this case, 10 minus 1 is 9. So what is our decision rule? So since alpha is 0.05, and we are using the lower-tailed t-distribution, because remember, we're interested in weight loss, our null hypothesis will be rejected if the test statistic is less than negative 1.833. Now, where did I get the negative 1.833 from? If you guessed the t-table, you are correct. So we go to our t-table, we find a one-tailed alpha level of 0.05, we go down to 9 degrees of freedom, and that is our critical value. So negative 1.833 is our critical value. So here is our hypothetical data. So we have our 10 subjects, and then we have W sub B, that's weight before, and then we have W sub A, that is weight after. Now what we do is we subtract them. It's just that simple. So our first subject had a weight before of 220 pounds, and then after the 12-month diet had a weight of 195 pounds. So that is minus 25 pounds, or that person lost 25 pounds. For subject 2, it was much more dramatic. That person lost 58 pounds. Subject number 4 didn't have any change at all. They actually stayed the same weight. If we go on to subject 10 actually gained 20 pounds. So you can see all we have here is the difference between the before weight and the after weight. Now the difference values, as on this red column here, form a distribution of differences in the same way a single sample mean have a sampling distribution. So this column, this D bar, if we found the mean of that column, that is a mean of the differences. So we go ahead and do that, and we find that on average, each subject lost 27.7 pounds. So we're just taking the mean of that difference column, which is negative 27.7 pounds. Now we also need to find the standard deviation of that column. So when we do that in Excel or whatever program we're using, we find that the standard deviation of those differences is 29.7 pounds. So we have our mean differences of negative 27.7 pounds and our standard deviation of 29.7 pounds. And again, all that comes from our column of differences. So let's go ahead and talk about the standard error of these matched pairs. So I'm just going to show you what the formulas are based on what you already know if you've been watching my videos up to this point. So remember that the standard error of the mean in the single population case was S sub x bar, that's the standard error of the mean, equals S, our sample standard deviation, divided by the square root of the sample size n. Now if you look at it for the matched pairs, it looks very similar because, well, it is. So S sub d bar, or the standard error of the difference, or the mean of the differences, equals S sub d, which is the standard deviation of the differences, divided by the square root of the sample size. So it's the same formula. Just on the left-hand side, we're using a single mean, and on the right-hand side, we're using a mean of differences. So what about the actual test statistic for matched pairs? So this is our formula for the single sample t-test. So remember, we have x bar, which is our sample mean, minus our hypothesized mean, which is usually 0, but not always, divided by the standard error, which, if you remember from the previous slide, was S divided by the square root of n. Now what about the matched pair t-test? Well, that looks very similar, doesn't it? Instead of x bar, we have d bar, which again is the mean of the differences, minus our hypothesized mean of the differences, which is usually 0. Again, all that's divided by our standard error. So if you look at the formula on the left and you look at the formula on the right, you will see that they are basically the same thing. The only difference is that we are using differences on the right. Now, it's also important to point out that each one uses n-1 degrees of freedom. So what about the actual interval estimate? Again, we will base this on what we already know. So remember, when we're estimating the mean of a population, we have a sample mean x bar plus or minus some margin of error, because that x bar is a point estimate, so it's never going to be perfect. That's why we have the margin of error component. Now for the matched differences, we have d bar plus or minus some margin of error. So the mean of the differences plus or minus that margin of error. Same basic structure. Now what about the actual margin of error component? So in the single mean case, we have t sub alpha over a, which is our critical value, times the standard error there in the red. Now on the matched measurement side, same thing. Our critical t times our standard error. It's important to point out that we're using alpha over 2 with our t, so that means it's two-tailed in this case. So we put all those together on each side, and our interval estimate in the single mean is x bar, our sample mean, plus or minus our t sub alpha over 2, which is our two-tailed t value, times the standard error. And that's with the degrees of freedom of n-1. Well, over here on the right, it's the same basic thing. So we have d bar, which is the mean of our differences, plus or minus t sub alpha over 2, same t value, times the standard error. But this is the standard error of the difference. So with the degrees of freedom of n-1. So I just want to compare what you already know on the left to what we're doing here on the right and show you that it's nothing dramatically new. We're just putting in different numbers based on this specific type of problem. So what is the actual weight in pounds at the critical t-value? So remember, this is our information here. Our sample size is n, and again, that's in pairs, so we have 10 pairs. The standard deviation of our differences, so S sub d, was 29.7 pounds. Now our confidence interval, as you can see over on the right, is what we just learned before. So d bar, the mean of our differences, minus t sub a times the standard error. Now, why is it just minus there? Well, remember, we're doing a one-tailed test. So we're going to be working in the lower tail of the distribution because we're testing if the weight is lower. Now here at the bottom of our chart, we can see our degrees of freedom are 9, our alpha is 0.05, and our critical t-value is negative 1.833. So we talked about all those before. So all we have to do is substitute this information into our formula. So we go ahead and substitute our t-critical of 1.833 there in the purple, times our standard error, which is 29.7 divided by the square root of n. We'll go ahead and calculate all this out. Now we'll pause here because that 9.39 is very important. What is it? Well, the 9.39 is our standard error. And I talked about this many videos ago. If there's one thing I could really get you to understand at a fundamental level, that would be what standard error is, because it plays such an important role in all of inferential statistics. If you really understand what the standard error is, you are well on your way to doing these problems correctly. But we'll go ahead and continue. We'll go ahead and do that multiplication. And what we have is d bar minus 17.22. So what does that mean in sort of real language here? So a mean of the differences representing a greater than 17.22 pound weight loss will lead to a rejection of our null hypothesis. So if we find all the differences in weight for each person, we calculate the mean of those differences. If the mean of those differences is greater than a 17.22 pound weight loss, we will then reject our null hypothesis and conclude that the diet program is a good one. So that is sort of the weight value in pounds at that t critical of negative 1.833. So the critical value and then this weight are two ways of pointing to the same thing. So let's actually go ahead and look at this on a curve. So everything we have here is from our previous slide. Let's go ahead and put our distribution up. So we have our 95% interval there in the middle in the upper tail, and then our 5% in the lower tail. So we have our hypothesized mean of the differences, which we think is 0 there in the middle. Our t-critical is negative 1.833. So you can see that the line between the rejection region and the non-rejection region falls at negative 1.833. And then we know that represents a pound value of negative 17.22, or 17.22 pounds of weight loss. Now let's go ahead and actually calculate our test statistic for this problem. So our sample size again is 10. So we have 10 pairs. Our mean of the differences was negative 27.7 pounds. So that was the average weight loss per person. Now the standard deviation of the differences was 29.7 pounds. So we have all the information we need to go ahead and calculate our test statistic. And again, all this came from our previous slide. So we have our degrees of freedom, we have our alpha, and our t-critical. So remember, here is our formula for calculating our test statistic. So all we have to do is substitute everything in. So we go ahead and do that. So we have negative 27.7 minus 0 divided by 29.7 divided by the square root of 10. Go ahead and continue our calculation. Remember our standard error, that 9.39? Well, there it is again. That's why I stress really understanding what the standard error is. So we have negative 27.7 divided by 9.39. Now, look at our t-critical. That's negative 1.833. Our test statistic is negative 2.95. So what does that mean? Well, our test statistic is well below our t-critical. It is therefore in the rejection region in our distribution. So here's where we left our graphic from before. So we have our test statistic we calculated, negative 2.95, We have our critical value here at negative 1.833, which of course represents a loss, an average loss of 17.22 pounds. So we have to go ahead and put our t-statistic, our test statistic, on the distribution. And of course it falls way down there, so negative 2.95. And that actually represents our mean weight loss of 27.7 pounds. So you can see that is well below our critical value. Now, since our test statistic is in the rejection region down here in the lower tail, what would happen to our hypothesis? Well, we would reject our null hypothesis because it is in the rejection region. Okay, so let's go ahead and find our interval estimate for this difference. So here's all the information we had before and the formulas we saw a couple slides ago. So our interval estimate, remember, was d bar, the mean of the differences, plus or minus t alpha over 2 times our standard error. Now our interval estimates are always two-tailed, so we're going to use the t alpha over 2. So now we just go ahead and substitute. So in this case, our d bar is negative 27.7. So that goes there where d bar is. Plus or minus our t critical, which is 1.833, times our standard error, which of course is 29.7 divided by the square root of our sample size. So we go ahead and substitute and calculate. We continue. So we end up with an interval estimate of negative 44.91 to negative 10.48, and again, that is in pounds. So our 95% interval estimate for this difference is a loss of 44.91 pounds to 10.48 pounds. That's our 95% confidence interval for the mean of the differences. Now what we ask ourselves, does this interval contain 0? Well, no, it doesn't. So this interval does not contain a mean of the differences that is 0. And again, that gives credence to us rejecting our null hypothesis. Now let's go ahead and look at how this works in Excel. Now I'm going to do a separate video on the paired t-test in Excel itself, but I just want to show you the output in Excel as it compares to what we've done in the video. So here's the t-test paired two sample means for this data. So you can see that the mean weight after the diet was 223.6 pounds. Before the diet, it was 251.3 pounds. Of course, then we have our variance and our number of observations, etc. Then remember in Excel, we set the hypothesized mean difference. Again, in this case, our hypothesized mean difference was 0. Then you can see DF. Well, that is our degrees of freedom. Again, it was n minus 1, which is 10 minus 1, which is 9. Now I'm going to mark out this bottom area because remember, we're doing a one-tailed test. So we're not interested in the values for the two-tailed. So I'm going to go ahead and just sort of mark through them so they don't distract us. Now the question is, how does the Excel output relate to what we did manually? Because it's a way to check that we actually did everything correctly and you can actually see on the distribution what is going on. Let's look at our critical value. So if we look at the Excel output and our graph that we did, we can see that they both say 1.833. So the t-critical one tail in Excel is 1.83311, etc. And of course we calculated the same thing based on our t-table. So we can see that those match. Now I will point out that Excel will always give you a positive t-value. It assumes that you know what tail you're working in. Now what about our actual test statistic, our t-statistic? Remember, we calculated it to be negative 2.95, which is there where the yellow circle is. Well, if you look in Excel, we have a t-stat, or t-statistic of negative 2.498, etc. And of course, ours was negative 2.95. We just rounded, so you can see that those are the same. So usually what happens is students learn how to do these in Excel, like we see here, but don't do a very good job of learning how to actually apply it and visualize it on the distribution. So I really wanted to put the two side by side so you can see the Excel output and what we did manually on the right. And of course, they both match. Now, I will point out too that the p-value, as you can see here in Excel, is 0.0081126664, etc. Now, that is well below our alpha level of 0.05. So what Excel is telling us is that the probability to the left of our test statistic, to the left of our yellow circle, is 0.00811, or 0.8 of 1%. Now, our critical value was at 5%, so it's obviously lower. So that's another way to show that we should reject our null hypothesis. So how can we state our conclusion? So based on our matched sample, the 95% confidence interval estimate of the difference between the matched pair means is negative 44.91 to negative 10.48 pounds. So that is the 95% confidence interval estimate for the mean of those differences in that column. So we are 95% confident this interval here contains the true difference between the before and the after weight. Now, does this interval estimate include the hypothesized mean difference of 0? No, it doesn't. So 0 is outside of this confidence interval, and the true mean of the differences appears much lower than just 0 pounds. So again, that gives credence to why we rejected our null hypothesis. So what is our conclusion? So we reject the null hypothesis that the mean of the before and after weight differences is 0. So the test statistic and D bar are both beyond our T critical value for the degrees of freedom of 9. Remember, we think it was negative 1.833, and our test statistic was negative 2.95. Therefore, based on this data, it appears that the diet works. Okay, so that wraps up our video on the matched samples t-test. So remember, what makes this different is that our samples are not independent of each other. Oftentimes, they are the same person or the same piece of equipment that we do a before or after analysis on. So we used examples of different training techniques. We used examples of machine software that gets upgraded. But the thing is that they are not independent. They don't always have to be the same person or same piece of equipment. They could be matched some other way, but they are not independent. But besides that, our ways of calculating all the test statistics are basically the same thing we've been doing. So just a few reminders and then we are done. If you're watching this video because you're struggling in a class, stay positive and keep your head up. Never let anyone else tell you you're not talented and smart, including yourself. Feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way when I upload a video, you know about it, and it's always nice to hear from you online. Just remember that the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person, that is what really matters. I firmly believe if you have the right learning process in place, the results will take care of themselves. So thank you very much for watching. I wish you the best of luck in your work and in your studies, and I look forward to seeing you again next time.